Upgrading an electrical service involves several key components. Let's consider upgrading a 200 amp service to a 400 amp service in a church setting. Firstly, regarding the placement of the current transformer, or CT, cabinet, it is generally acceptable to install this outside. This external placement offers easy access for utility personnel to read the meter. It also provides a degree of environmental protection for the metering equipment. Secondly, the meter itself should be installed within the CT cabinet to accurately measure the electrical load being consumed. Moving to the interior components, consider the I-line panel board. Yes, installing an I-line panel board inside with a 400 amp main breaker is a viable option. This panel board then serves as the primary distribution point for the building's electrical system. Existing fuse boxes can be refed from this new I-line panel board. This allows the existing circuits to be powered from the upgraded service. Installing a new 200 amp panel for the addition is also an acceptable practice. This dedicated panel will provide power to the new circuits required by the building addition. To summarize the complete setup, firstly, a CT cabinet containing the meter is installed outside, providing utility access and environmental protection. Secondly, an I-line panel board with a 400 amp main breaker is installed inside to act as the main distribution panel. Thirdly, the existing fuse boxes are refed from the I-line panel board, ensuring continuous power to the existing circuits. Fourthly, a new 200 amp panel is installed to supply the circuits in the new building addition. It is absolutely crucial to remember that all electrical work must strictly adhere to applicable electrical codes and regulations. A licensed electrician must perform the upgrade. They must also secure all necessary permits before commencing work. For a 400 amp electrical service upgrade, several factors must be considered to ensure a safe and compliant installation. Firstly, the service entrance conductors must be appropriately sized for the 400 amp service. This involves selecting conductors with an ampacity rating sufficient to carry the anticipated load, as specified by the National Electrical Code, or NEC. Table 310.16 provides ampacity ratings for various conductor types and sizes based on insulation temperature rating and installation conditions. Secondly, the overcurrent protection for the 400 amp service must be carefully selected. Typically, this involves a 400 amp main breaker in the I-line panel board. The breaker's interrupting rating must be sufficient to handle the available fault current at the service entrance. Utility companies can provide information on the available fault current. Thirdly, the grounding and bonding system must be properly installed to ensure electrical safety. This includes grounding the neutral conductor at the service entrance and bonding all metallic enclosures and equipment to the grounding electrode system. Article 250 of the NEC provides detailed requirements for grounding and bonding. Fourthly, the CT cabinet and metering equipment must be installed according to the utility company's specifications. This typically involves specific requirements for the enclosure type, mounting height, and wiring methods. Coordination with the utility company is essential to ensure compliance. Fifthly, the I-line panel board must be properly sized and configured to accommodate the existing and new circuits. This includes calculating the total load on the panel board and selecting the appropriate number and size of branch circuit breakers. Article 220 of the NEC provides guidelines for calculating electrical loads. Sixthly, when refeeding the existing fuse boxes, the existing wiring must be evaluated to ensure it is adequate for the intended load. If the existing wiring is undersized or in poor condition, it should be replaced with appropriately sized conductors. Seventhly, the new 200 amp panel for the addition must be installed according to the same standards as the main panel board. This includes proper grounding, bonding, and overcurrent protection. Eighthly, all wiring connections must be made with approved connectors and terminals. Connections must be talked to the manufacturer's specifications to ensure reliable electrical contact. Ninthly, the installation must comply with all applicable local codes and ordinances. These codes may have additional requirements beyond those specified in the NEC. Consulting with the local electrical inspector is recommended. Tenthly, a thorough inspection and testing of the completed installation is essential to verify its safety and functionality. This includes testing the grounding system, verifying the voltage and current at various points in the system, and checking the operation of all circuit breakers and other protective devices. The selection and installation of conductors for a 400 amp service requires careful consideration of several factors to ensure safety and compliance with the National Electrical Code. Firstly, conductor ampacity is a crucial consideration. The conductors must have an ampacity rating equal to or greater than the maximum load they will carry. NEC Table 310.16 provides ampacity ratings for various conductor types and sizes based on insulation temperature rating and ambient temperature. For a 400 amp service, conductors with an ampacity of at least 400 amps are required. Secondly, conductor type plays a role in determining ampacity. Copper conductors generally have a higher ampacity rating than aluminum conductors for the same size. The choice between copper and aluminum depends on factors such as cost, weight, and environmental conditions. Thirdly, insulation type affects the allowable ampacity. Conductors with higher temperature ratings such as THHN or XHHW can carry more current than conductors with lower temperature ratings such as TW. The insulation type must be suitable for the operating temperature and environmental conditions. Fourthly, ambient temperature correction is necessary when the ambient temperature exceeds 30 degrees Celsius, which is 86 degrees Fahrenheit. NEC Table 310.16 provides correction factors for different insulation types and ambient temperatures. These correction factors must be applied to the conductor ampacity rating. Fifthly, conductor dirting is required when multiple conductors are bundled together in a conduit or cable. NEC Table 310.15.3 provides dirting factors for different numbers of conductors. These dirting factors must be applied to the conductor ampacity rating. Sixthly, voltage drop must be considered to ensure that the voltage at the load is within acceptable limits. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. The voltage drop can be calculated using the formula voltage drop equals current times resistance times length. Seventhly, conductor size is determined by the ampacity, insulation type, ambient temperature, dirting factors, and voltage drop requirements. The conductor size must be large enough to carry the anticipated load without exceeding the allowable temperature rise or voltage drop. Eighthly, conduit size must be sufficient to accommodate the conductors. NEC Chapter 9 provides tables for determining the maximum number of conductors allowed in different conduit sizes. The conduit must be sized to allow for easy installation and removal of the conductors. Ninthly, conductor material, either copper or aluminum, should be selected based on factors such as cost, weight, and corrosion resistance. Copper conductors are more expensive but offer better conductivity and corrosion resistance. Aluminum conductors are less expensive but require larger sizes to achieve the same ampacity. Tenthly, conductor termination methods must be appropriate for the conductor material and size. Approved connectors and terminals must be used to ensure reliable electrical connection. Connections must be torqued to the manufacturer's specifications. Selecting the appropriate overcurrent protection for a 400 amp service is crucial for ensuring electrical safety and protecting equipment from damage. Firstly, the main breaker must have an ampacity rating of 400 amps to match the service capacity. This breaker serves as the primary overcurrent protection device for the entire electrical system. Secondly, the main breaker's interrupting rating, or AIC, must be sufficient to handle the available fault current at the service entrance. The AIC rating indicates the maximum fault current that the breaker can safely interrupt without failing. Utility companies can provide information on the available fault current at the service entrance. Thirdly, the main breaker should be a molded case circuit breaker, or MCCB, which is designed for high current applications. MCCBs are more robust and reliable than standard circuit breakers. Fourthly, the main breaker must have appropriate trip characteristics to protect against both overloads and short circuits. Overload protection is typically provided by thermal magnetic trip units, which respond to sustained overcurrent conditions. Short circuit protection is provided by instantaneous trip units, which respond to sudden high current faults. Fifthly, the main breaker should be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or all. This ensures that the breaker has been tested and certified to meet industry safety standards. Sixthly, the branch circuit breakers in the panel board must be sized appropriately for the circuits they protect. The breaker size should match the ampacity of the circuit conductors and the load served by the circuit. Seventhly, the branch circuit breakers should also have adequate interrupting ratings to handle the available fault current at their respective locations. The interrupting rating can be lower than that of the main breaker, depending on the impedance of the circuit. Eighthly, the branch circuit breaker should be of the same type and quality as the main breaker to ensure consistent performance and reliability. Ninthly, surge protection devices, or SPDs, can be installed at the service entrance to protect against voltage surges caused by lightning or other transient events. SPD divert surge current away from sensitive electronic equipment, preventing damage. Tenthly, ground fault circuit interrupters, or GFCIs, should be installed in circuits serving wet locations such as bathrooms and kitchens. GFCIs detect small ground faults and quickly interrupt the circuit, preventing electric shock. The grounding and bonding system is a critical component of any electrical installation, ensuring safety and minimizing the risk of electric shock. Firstly, the grounding electrode system must be properly installed to provide a low impedance path to earth for fault currents. This system typically consists of a grounding electrode conductor connected to one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes. Secondly, the grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. The grounding electrode conductor must be securely connected to the grounding electrodes using approved connectors. Thirdly, the neutral conductor must be grounded at the service entrance to establish a reference point for the electrical system. This is typically accomplished by connecting the neutral conductor to the grounding electrode conductor at the main panel board. Fourthly, all metallic enclosures and equipment must be bonded together to create a low impedance path for fault currents. This includes bonding the metal enclosures of panel boards, junction boxes, and equipment to the grounding electrode system. Fifthly, the bonding conductors must be sized according to NEC Table 250.122, based on the size of the circuit conductors. The bonding conductors must be securely connected to the metallic enclosures and equipment using approved connectors. Sixthly, metal water pipes and gas pipes must be bonded to the grounding electrode system to prevent them from becoming energized in the event of a fault. This bonding is typically accomplished by connecting a bonding jumper to the pipe near the service entrance. Seventhly, separately derived systems, such as generators and transformers, must have their own grounding electrode systems. These systems must be grounded and bonded according to the same requirements as the main service entrance. Eighthly, the grounding and bonding system must be inspected and tested to verify its effectiveness. This includes measuring the impedance of the grounding electrode system and verifying the continuity of the bonding connections. Ninthly, any modifications or additions to the electrical system must be carefully evaluated to ensure that the grounding and bonding system remains effective. Changes to the wiring or equipment can affect the grounding and bonding system, potentially compromising safety. Tenthly, the grounding and bonding system must comply with all applicable codes and regulations. The NEC provides detailed requirements for grounding and bonding, which must be followed to ensure safe and compliant installation. Regarding the installation of the CT cabinet and metering equipment, it is vital to adhere to both the National Electrical Code, NEC, and the specific requirements of the local utility company. Firstly, the location of the CT cabinet must be accessible for utility personnel to read the meter and perform maintenance. The cabinet should be mounted at a convenient height, typically between 4 feet and 6 feet above ground level. Secondly, the CT cabinet must be weatherproof and suitable for outdoor installation. It should be constructed of durable materials, such as stainless steel or aluminum, to withstand environmental conditions. Thirdly, the CT cabinet must be properly grounded and bonded to ensure electrical safety. The cabinet should be connected to the grounding electrode system with a grounding electrode conductor sized according to NEC table 250.66. Fourthly, the metering equipment must be installed according to the utility company's specifications. This typically includes specific requirements for the wiring methods, conduit types, and conductor sizes. Fifthly, the CT must be installed correctly to accurately measure the current flowing through the service conductors. The CT should be installed around the ungrounded conductors with the correct polarity orientation. Sixthly, the meter must be properly calibrated and tested to ensure accurate measurement of energy consumption. The utility company typically performs the calibration and testing of the meter. Seventhly, the wiring from the CT to the meter must be shielded to prevent electromagnetic interference. The shielded wiring should be installed in a separate conduit from other wiring. Eighthly, the CT cabinet and metering equipment must be protected from physical damage. The cabinet should be mounted in a location where it is not likely to be struck by vehicles or other objects. Ninthly, the installation must comply with all applicable codes and regulations. The NEC and the utility company's requirements must be followed to ensure a safe and compliant installation. Tenthly, the installation should be inspected by the utility company to verify that it meets their requirements. The utility company may also require the installation to be inspected by a third-party inspection agency. When sizing and configuring an I-line panel board, several key factors must be considered to ensure proper operation and safety. Firstly, the panel board must be sized to accommodate the anticipated load. This involves calculating the total connected load of all the circuits served by the panel board. Secondly, the panel board should have sufficient spare capacity to allow for future expansion. A general rule of thumb is to provide at least 20% spare capacity. Thirdly, the panel board must have an adequate interrupting rating to handle the available fault current at its location. The interrupting rating should be equal to or greater than the available fault current. Fourthly, the panel board should be listed and labeled by a recognized testing laboratory such as Underwriters Laboratories or all. This ensures that the panel board has been tested and certified to meet industry safety standards. Fifthly, the panel board should be installed in a location that is accessible and well ventilated. The location should be free from moisture, dust, and other contaminants. Sixthly, the panel board should be mounted securely to a wall or other supporting structure. The mounting should be strong enough to support the weight of the panel board and its contents. Seventhly, the panel board should be properly grounded and bonded to ensure electrical safety. The panel board should be connected to the grounding electrode system with a grounding electrode conductor sized according to NEC table 250.66. Eighthly, the panel board should be equipped with a main breaker to protect the entire panel board from overcurrent. The main breaker should be sized according to the service capacity. Ninthly, the branch circuit breakers in the panel board should be sized appropriately for the circuits they protect. The breaker size should match the ampacity of the circuit conductors and the loads served by the circuit. Tenthly, the panel board should be labeled clearly to identify the circuits served by each breaker. The labeling should be durable and easy to read.